Okay, so we said there was more potential energy than just gravitational potential energy. One of those is the gravitational potential energy of a spring. And I'm going to go ahead and give you the formula. It's just 1/2 of the K value times x squared. All right, now this one's a little bit more complicated because K is equal to the spring constant. And its units are just going to be newtons per meter. X is equal to the distance the spring is displaced from rest. I know, that sounds complicated, but it's not. It's not too bad, okay? What you need to remember, though, is a constant is going to stay constant. But just like the constant for friction, it differs from every single spring that exists. That means it has to be laboratorily tested in order to figure out what your K value is going to be of a spring, okay? So that part you have to get through laboratory testing, and then the distance is simply a measure in meters of what you're going to get. So let me also put that, I guess, is the units for that are meters. And that should do that. So the way we use that is imagine you have a spring and a block, but before you let the block drop, you measure just the distance of the spring. So the spring isn't pulled or pushed in any direction. It's just at its normal, how it sits with nothing on it. Well, that's going to be an x distance of 0. So that's its distance at rest. So the x naught is what they call that. And so if you were going to calculate this, it's going to have no potential energy because that x value is a 0, which means all of that multiplied is going to be 0, so it's 0 joules. Now, that being said, you can come along and you can then have that spring sprung out, right? And after it gets sprung out to a certain distance, you would measure, so if this was at rest, right? So that's x naught. You would then measure the distance that it's moved. And that is your x value, okay? And let's just say that that's equal to, let's do something simple. Let's say it managed to move 0.5 meters. And that's still a huge distance, but maybe this is a huge spring. We don't know. Okay, anyway, if I'm doing that now, I would be able to figure out its potential energy only if I also know its K value. And so let's say that we laboratorily tested and found out that K for this spring is equal to, let's say 2, okay? Now, our units for that are Newton meters. So let's say it had a K value of 2 newtons per meter, okay? All you would do is you would come in and say, well, I want to know the potential energy of this spring pulled to that point, and you do 1/2 times 2 newtons per meter times 0.5, it's a terrible 0.5 squared, and that is meters there, right? And so you'd have to square the meters first. If you don't remember that, you need to remember your order of operations. You have to do an exponent before you can multiply across. So you would have to square your 0.0 or 0.5, and so you'll get just 0.25, and then you multiply across. And essentially that's just going to be 1/2 of 2 is 1, and so it's going to be 1 times 0.25, and you'll get that the potential energy of that spring is 0.25 joules, right? And that's easy peasy if someone's done the hard work and already gotten the K value for you. But let's see how you could clinically figure out or laboratorily find out what that K value is. To do that, we need a better understanding of what that K value is. So essentially, that K value is just the slope of two individual things. As you apply a force, how much does it stretch, right? So if we do a graph where we apply a different force to our spring and we figure out how much from x naught it stretches and we plot those points on it, hopefully we would get a fairly linear explanation. So at 0, 0, it shouldn't move at all, right? No force should be at x naught. And then as you apply them, hopefully they're coming up just like that. And as you can see, you should be trying to get a straight line. A straight line is going to have a slope, right? So the slope would be equal to force over x, which is equal to a Newton over a meter in value, right? So that's how you actually clinically get that. Now the problem is, most of the time you don't have such clear-cut things. Our instrumentation, by the way, is very poor with what we have in the classroom, so you might get more things that look like this. Now that wouldn't be great, but the more of them that you get, hopefully the more you would start to see a trend line. And so if you figure out your trend line, it should make up a little bit for all of the kind of crappy error that you have in your instrumentation, and you should be able to get a reasonable K value. So let's go ahead and find this a little bit confusing for people. So we'll go ahead and take that out and write it was K. That's what you get with that. Your K value is your slope there. So if you take something like a rubber band. A rubber band is a type of spring. It's an elastic spring, but it's a spring. And so let's say that we have a rubber band over here, and we attach it to a bar, and we have our rubber band hanging down, okay? So there's our rubber band. Now, we would go ahead and mark where it is with nothing measured, and that's going to be our x naught. That's our starting point, right? And then you come and you attach some sort of mass to the bottom of it. So let's have the scenario again where we take that, and now we have our rubber band. It's going to be stretched a bit more this time, because this time we have, let's say, a 1 kilogram mass attached to it, right? And we can very well see that if this was x naught, then this value is our x. And let's say we just got something very small. Let's say we got, we'll probably do it in centimeters, so let's say we do 2 centimeters, okay? Well, we can get one of our plot points from this. We're going to get our force value by taking the mass that we have and multiplying it by that little gravity, because that's what's going to be pulling it down. And we would get in this case that it's 9.8 newtons total, and that would be one of our plot points, or one of our coordinates, right? And then we just need to change our centimeters into meters. Luckily, there's 100 centimeters in a meter, and so we would get that our x distance is equal to 0.02 meters. And we could then go in and make that our plot point. Our plot point, of course, for that being our x-axis would go to 0.2, our y-axis would go to 9.8. And if you do a whole bunch of those, you could get this. So you just want to keep changing the mass, keep measuring how much it changes, and you can get your graph that you can find a trend line and be able to get a slope from, which will be your K value. That way you yourself can clinically trial these different springs and rubber bands and things like that to figure out what kind of energy it can store. and with what kind of energy it can store, you know how far you have to pull it back to go at a certain speed or to a certain height. And so you can calculate all kinds of things with that.